Hi everybody, thank you for coming to this talk. So my name is Matthias Bräger and I'm working for CERN since 8 years already, and I'm responsible for C2MON, which is stands for Controls and Monitoring Platform at CERN. And we use that monitoring platform for a project called Technical Infrastructure Monitoring, and it's basically the base of the service. And this platform has been developed 4 years ago because we didn't want to reinvent always the wheel about data acquisition. And I don't know if you followed this morning the talk, the Velo keynote speak talk. I mean, that's really a great platform. And what they are about to do is what he said, the acquisition layer. So basically, you could combine C2MON easily with Velo, as you will see later, because it attacks exactly that problem about data acquisition in a large distributed environment where you have different protocols and different services, and so where you end up very often in a configuration hell with a lot of different configuration files lying a bit everywhere. So, and we try to attack that. So this is just a bit about myself. So before I was working for CERN, I have spent 2 years at a company called Logica, which has a space department in Darmstadt, and there we were subcontractors for ESOC, which is the European Space Operating Center, and we were helping out with making the Galileo satellite project. But as you've seen, Galileo is still not up in the air or in space, so it got a bit boring for me and I went then to CERN. All right, so before I will dive into C2MON, I would like to spend a bit on CERN itself, because I know that many people are really interested what's going on at CERN, and they know that we are dealing with a lot of big data sources. So it has been funded over 60 years ago, 1954, just to give physicists around the world like a peaceful, neutral place to work and study the nature of the smallest particles in the world. And we have 21 member states currently, and we are around 3,300 staff members, but in total there are always like 10,000 people on site, so physicists around the world, doctoral students and so on, who work at CERN with a large Hadron Collider. The budget is around 1 billion Swiss francs, and half of it is for the payment of all these people, and the rest goes then into the technical equipment. You might ask yourself, well, that's quite a lot of money for fundamental research, so what's the outcome? And basically, there's a lot going on. For instance, the World Wide Web protocol was invented by Tim Berners-Lee, which worked at that time at CERN. So it's, again, something that was started at CERN for the physics community, but as a side product now, everybody uses it. And there are a lot of examples like that. We have a long history in collaboration with hospitals and medicine, because, for instance, computer tomography was something that was studied, first of all, for the detectors at CERN. And now there are around, I think, 15 Hadron therapy cancer centers around the world. Well, this is also very related to what we are doing, the Hadron Collider. So the technology is shifted to the industry. And I just want to show you, I hope that switch works. Yeah. We have a webpage called Knowledge Transfer, And here you can have a look what we are offering. So for instance, there's a license called Open Hardware License, which was started by CERN to share blueprints basically of hardware. And so to give something equivalent to open software. And there's, for instance, one very interesting project which is quite successful, is this White Rabbit solution. This is basically a little hardware piece that you can put in your device, and it's to synchronize on nanoseconds precisions a lot of physical devices. So in a big distributed system, you might need that. All right, so that is just to mention that. And there's also, like, if you want to make a spin-off of technology coming from CERN, there's also funding going on. So have a look on that site if you find something interesting. So this is basically what CERN is about. It's about the LHC, which is sitting 100 meters under the ground, and it's the world's biggest machine. And it generated in 2012 30 petabytes of data. And we stored at that time already around 100 petabytes in total. I'm giving that number from 2012 because there was a technical stop and it has been upgraded, the whole machine, and now it can run with a double energy like before. So it means also doubling the amount of data that needs to be stored. And so it started in 2010 with 3.5 tera electron volt, and now we are, and then it was like ramped up to 4 tera electron volt. It's not speaking also to me because I'm a computer scientist and not physicist, but just to give you an impression about then the energy and the data rate, because now after this shutdown and the upgrade, now we restarted and we are able to inject beams with 6.5 tera electron volt in every direction. So it means they collide then with 13 tera electron volt. And that creates a lot of data. So this is the biggest machine, the biggest collider, if you like. There are 4 of these on the LHC, and it has 100 million channels, so basically 100 million sensors which can produce data that needs to be then recorded. And it has a collision rate of 40 megahertz, and it generates 1 petabyte per second. So not gigabytes or terabytes, it's petabytes. So nobody, even at CERN, we're not able basically to store this amount of data. So what you have to do is filtering. And so there are 3 layers of filters. There's a hardware filter, basically, that filters already most of the data. And basically what the machine does, it's making pictures of collisions, 3-dimensional pictures. And these pictures, we want only to save those which are interesting. So basically where we could discover new particles. So we don't want to explore what is already known in the physics. We want to explore what is new. And this is why we have the filtering, these hardware filters, and then software filters, which is basically a distributed grid around the world where we send these jobs and they analyze a bit in deeper these pictures, and then they decide if that is relevant for storage or not. So I don't know, there's a little riddle in this picture. Do you see a guy here standing? So he's there. So just to give you the size of that thing, which is, I think, if I'm not wrong, around 46 meters in height. So it's like a 6-row building, you can say. So, but this is just one. The LHC is just the biggest ring of 9 rings that exist at CERN, and they all are connected together. So the guys at CERN, they're also called Lord of the Rings. So I'm not explaining in detail how it works, but basically the journey starts somewhere with a little hydrogen bottle where you extract then protons, and then you send them on their journey until they reach the LHC and have enough energy to be collided. So when we talk about big data at CERN, we have different areas of big data. So the biggest amount is the physics data, this 100 petabytes. And, but there's a lot around that, because this is just the essential then for the physicists. This is what they are interested in. But we are more a service provider, and my job is among a lot of other people to assure that this machine is running as well, as often as possible. And so we have to assure basically that the service is constantly available. And so we produce a lot of log data around that. Configuration data is a big source of data. Metadata of the physics data, so basically to know which sensor has captured the data and for which experiment. And another big source is sensor data of the technical installation. So you can imagine that this big machine has a lot of technical equipment, and those things needs also to be monitored. And this is more my domain. So I'm not related to physics data. It's more about this sensor data of the technical installations. And so another question to you, where do you think that we store this data? Do you think that we use Hadoop for this? So please raise your hand if you think that Hadoop is where physics data is stored. Well, apparently you don't think that this is the right technology. So is it, I don't know, solid state drives, or maybe the cloud? Well, to give you the answer, it's just plain old tapes. And there's a simple reason for that. It's just because it's such a big amount of data. I mean, you cannot really provide so many hard disks. And what we do is like a two-tier architecture that we use tapes really to just store this data that comes in. And normally the physicists, they don't need them live. They come maybe 2 months later and say, okay, now I want to get a certain set of data. And then they can wait for several minutes and take a coffee before it's there. And what we do then, we shift this data to disks again. So we have a big disk pool, and this is where the most used data is stored, basically. But we use Hadoop for the metadata of the experimental data. So this is then basically the catalog to browse then the data. So the physicist would then use this catalog to identify what is really interesting for them, which data sets they want to look at for their specific theory that they have in mind. And then with this metadata, we are able to retrieve again from the tapes the data, the physics data. So to handle all that, it's quite demanding. We need 100,000 processors just to receive this data and then to store them on tape. What you do normally then is you flush them into, you load them into RAM, and then you flush them to the tape, because the tapes are really fast in writing, much faster than you can write to a disk. This is also quite interesting. That's why you cannot have them on disk and then somehow stream them to tape. You have to have them in RAM and then to flush them. So we have peaks of 6 gigabytes per second that we have to write to tape. So if you miss 1 second and you're not able to do that, well, then you have 12 gigabytes to handle in the next, because the most, let's say, the disaster which can happen is that you lose this precious data. So this is all what we are for which we are employed is to assure that none of this physics data is lost. Yeah. So in run 2, now we are attempting to have peaks of 10 gigabytes per second that we have to write. And of course, this requires then more tapes and so on. And what we play with Moore's law, that the density is doubling every 2 years. And till now, we win the game. So what we do is we replace old tapes by the newest generation. And like that, we manage with the same amount of tapes to keep more and more data. So we have, then I said we have now freed 140 petabyte of tapes waiting for the run 2. And we have a total disk space of 45 petabytes. What you see here is like this tape robot that we use, and it's quite, if you manage to come and visit CERN, I mean, everybody is free to see that, and there are then tours to really see the big server farm that we have. It's quite interesting. So why tape storage? I mean, it's because the cost of tape is a lot less than disk storage. And well, and if you don't need your data, it doesn't consume any electricity. So it's again a cost reduction. Yeah. And then another thing is that tapes are more reliable as a storage than a disk. So that's normally in Hadoop. What you do, you would copy twice your data, so you would keep 3 copies of your data distributed. It's normally the setup what you do. And in tape, you only need to have 1 backup. That's normally sufficient. And with the amount that we have, having to triple the amount would be quite challenging. Okay, and right. So that was about the introductional part about CERN and the physics data. So now I want to show you a bit more what we do with the sensor data about all that. And we have a lot of systems to control at CERN. I mean, starting from controlling the computers, about the electricity, cryogenics, and the magnets of the LHC, because to bend the beam into a circle, you need really strong magnets, and all that needs to be surveyed. Then, of course, there's a big safety aspect. You don't want that anybody is inside the tunnel when the beam is running. It's because during the collisions, there's radiation that occurs, and safety goes first. So we have the same strict safety rules like a power plant. Even though when you switch off the LHC after 20 minutes, you can go into the tunnel without getting a risk to get radiation. So in total, we have like 85,000 devices to control with around 2 million endpoints, so meaning sensors. And it's even much more when you would include from these even the subsystems. And all that needs at the end to be controlled from one control system, from the control center. And this is a quite interesting place to be, because when you enter, it's like it has 4 big islands, and there's always people around 24/7 and controlling the LHC. And it's a quite complex infrastructure. So this is basically a little drawing about how everything is playing together. And we have each dot is a process or a device, and each line is a network connection. And very often the data is coming from very small units. So this is a PLC. I don't know who has already worked with this kind of systems. Okay, yeah, good. And so real-time data comes very often from there. So you have your analog basically what they do is they transform your analog sensors, analog signals into digitized signals. And so they can basically produce a lot of data. So very often it's also then not everything is relevant, but it's just because it's an analog wave that they try to reproduce. So a temperature sensor, for instance, can then send constantly new output, but sometimes it's just like 6 digits after the comma that something changes, which is not so interesting. So a challenge is then to filter out relevant information. But what might happen is then that you end up in a configuration hell, because you have many different types of data sources and protocols, and because in a big environment, industrial environment, you have normally not only one system, one SCADA system, or except if you buy maybe everything off the shelf from one vendor, but normally you have more really distributed environment. So you have to face then configuration, how to get your data from these different systems into your system for making analytics. Or then you have to deal with this complex data structure and the addressing of, for instance, the low-level devices. And then data might have different data rates. So if you take a door state, for instance, which is normally Boolean and it tells you it's, the door is open or it's closed, well, a door is not constantly reopened and closed. So your data might, the data flow of a door state is normally very small, yeah, compared to a temperature sensor. But in your end product, in your application, you want to have normally all your latest sensor data at once. So this is a challenge. And so we thought then, what if there would be a platform that handles all this low-level data subscription for you, so that from when you make your new application, that you don't have to care anymore from where it's coming, whether it's coming from a PLC or an OPC or another program. So that shouldn't be relevant for the UI, let's say, programmer. And but then you have also to monitor all these different data sources and reconfigure. And what you want also that a platform then reconfigures your acquisition processes at runtime. So meaning all of a sudden you want to have more data from a certain system. So there must be somebody who has knowledge about how to get the data from, for instance, from your PLC. He has added a new cable to a sensor. So this needs then to be injected into the configuration. And if that platform could also standardize messages and the data storage in the end from you, from these different input channels, that would be quite convenient. So, and normally, because when you have an end result, then on your client here, it would be great if the data rate would be already reduced, because you're talking then just to one computer and not yeah, and so the distributed system below should already lower the data streams to the relevant information. So, and basically, this is what we did in the end with C2MON. Oh, sorry, I went a bit fast. So with C2MON, we provide all that, and we provide then custom data streams to the end application. And we allow to store all the data and the history into different data stores. And this is then used, this platform, for different monitoring problems at CERN. So really, because this is a reoccurring problem that which had to be always resolved at CERN, and instead of seeing yet another monitoring appearing, we said, okay, let's do something together and let's create such a platform. And so there are many use cases then what you can do with that. You can feed, once you have unified your data streams and you can set up custom channels of data streams, then you can feed that to your analytics engine, for instance. So to make publicity for Velo would be perfect, yeah. So because all the low-level subscription is handled and the monitoring of these devices. So when I don't know who of you has used Elasticsearch? Almost everybody, great. But normally, do you use that also for time series data? Few. Because it's great also for time series data, and it's not so much used at the moment. And so what we do is, because we structure the data and we annotate then later on the data with metadata, your custom metadata, you get a great platform with nice graphical front ends like Grafana and Kibana to make already custom dashboards without that, well, and everything is open source, and you get really nice results, which I will show you in a few seconds. But you could use then also C2MON to realize something like Internet of Things, or what I like more to talk of is Intranet of Things, because I think first you have to be more clever in your own company before you can think about Internet of Things. Yeah? And very often it's you need something to talk between your different isolated, let's say, systems. And C2MON is great because it could be in the middle to communicate between these different systems. So it's a modular and scalable layer. So you can basically, it's a 3-tier architecture, first of all. And it starts with a data acquisition layer on the bottom. And basically, for every protocol, you can set up an acquisition module. And you can have as many as you want of them, and you can scale that out. And then we have what we call the business tier. This is basically where then the different streams of the different protocols arrive, and at that moment they're already harmonized. So it's the DAC API which takes care that your data is in the end unified. And it already handles on that layer all the filtering logic. So because we think that it's good if you filter already at the very beginning to the relevant information, because if you would first store all this data to tape or to disk, this is first of all also a cost factor. So big data is a cost factor if you don't make sense out of it. And you have to buy the hardware, you have to store everything, and it only makes sense if you have an output that then brings benefit to this investment. So, but if you would filter out your incoming data already before you store it, you would need less disks and capacity to store this data. Right, so at the moment we have 2 big systems running at CERN on it, which is TIM, for which I'm responsible for, and Diamond, which is more to monitor all the IT infrastructure and front ends. And there's a third about to be migrated. It's the central LHC alarm system. So this is basically where the operators see then the alarms that cannot be handled automatically and which needs intervention by human intervention. And So the system is about to get open source, and we are looking for outside collaboration for an early stage. It's not yet on GitHub. I hope that by the end of the year we will manage that, but it's a huge effort, and we want to make it right or not at all, in the sense that we want to have a professional appearance, and this requires a lot to make a neat packaging, to provide, for instance, Docker images, or then, of course, to invest a lot in your documentation. And that is quite time-consuming, but we are slowly getting there. So, yeah, this is just to show you that the server internally uses in-memory technology, distributed in-memory technology, which allows you to cluster the C2MON servers, and basically like that they become stateless, and you could restart them to make, for instance, rolling updates. This is what we do, and this allows you to achieve high availability within your system without bringing the whole service down. So what we keep in memory is only the configuration and the metadata of the sensors, and the latest sensor values. And everything with this history goes then into Elasticsearch or in a relational database. So basically at runtime, we are not dependent on the database itself, because the clients which use then the C2MON client API will retrieve the latest sensor values directly from in-memory, which is also much faster than retrieving it from the historical backup. And in general, we made really good experience with in-memory technologies, and I can just encourage you to also look at it, because nowadays there are many open source products and also industrial products which allows you to, I see that it's a bit bad here, the resolution. Okay, but basically when you start thinking about it, normally you have everything in your NoSQL store or your relational database, so you start with an application which is fully dependent on your database. And normally how you start with is that you put your most important information that you need constantly in memory. And if that works well for you and you get trust with it, then normally you can put more and more. And now these technologies, they allow you to use the off-heap basically or they don't use the JVM memory, they use the off-heap memory, which allows you to use the full RAM in your machine, which is very powerful because also it's not affected by the garbage cycle. So normally you have a limit of 4 to 6 gigabytes when you run your JVM, and you shouldn't go over it because of the garbage collection cycle. But I'm not really an expert of that, so I don't know if in Java 9 with the new garbage collection that problem will be solved, but that's currently what it is. So this is just to show you a bit what's available, and if you're interested, we are currently using EHCache and Terracotta, but what is very nice is Apache Ignite, which started. It's a young product from Apache, but there's a company, GridGain, I think, behind, and they made it open source. And well, have a look at it. It's very nice technologies. All right. So now, just to explain you a bit more what C2MON internally, what it uses as a configuration structure. So when we call about sensors, we call about tags, but you can see a tag as an envelope where you send then your data. So normally it would be really like raw data formats like long string booleans, but you can also put more complex objects in it or your arbitrary objects. And in the end, what we do with the data once they are retrieved from the sensors is that they all appear the same. They have all a unique ID and a name. And of course, they have a value, whatever that is. And they have a source timestamp. And they come with a quality flag. So this quality means if the C2MON system is still able to retrieve that data, or if there's a problem in the connection. And in that time, it would change the quality to bad, and it would give you an explanation what is going on in your system. And we have like 3 types of tags. And what we have, one is the control tag, which is more internally used to give you the availability of the different equipments. And then the data tags, which are then for the data acquisition. And then we have a very simple rule DSL to make a bit more sense about your data, but it's not at all comparable to what Waylo gives you. It's a really simplified rule engine, which is there already for many years. Right. So this is how it would look like to just subscribe to a stream. Basically, from the client API point of view, you just get a tag service, and you can subscribe by name. And basically, then on your listener, you can then deal with your tag information, so the real time. And if you want to subscribe to a custom stream of data, basically you can play with wildcards and then subscribe to many sensors. And this wildcard can be placed, also you can combine them, and like that it gives you a lot of possibilities to like filter down on which data you are interested in. And these names that you give to your text, this is fully customizable for you. So if you have a very clever pattern inside your naming structures, it gives you a lot of possibilities. And it's good to think about the name, because then later on in Elasticsearch, for instance, you can also search on these names. So the process, this is just on the acquisition layer. The DAC process then takes care of the equipment monitoring and even sub-equipments. For instance, think if you have, I don't know if you know that server, but there's an OPC server, which is an industrial standard, and below you would have PLCs, so everything could be monitored. So what we do then on the DAC layer, we have different filtering strategies that you can apply, and everything can be customized on your tag. So basically, this is normally what the expert would do. He would introduce a new sensor, and then he would define also what would be the min-max value, or the value dead bands, and so on. So the basic configuration structure is a bit more complex in the sense that you have then data tags that you can attach to your equipment or to your sub-equipments, and then you can add metadata information to your tags and alarms. And all that is configurable through a simple build-in pattern on the client side. And we have something which is called the configuration service. And now to create just a new process, which is a single a Java process that would run somewhere in your network. To configure that in C2MON, you would just run that command, create process, and you give it a name. This is then the name which allows then the process to retrieve its configuration from the central server. So basically then C2MON would create a new process. And then you have to define which protocol he should support. So we have different types of protocols. Here I chose the REST protocol, which allows you to do gets and posts. So it, basically here you could inject your own protocol very easily. So we have an API on the DAC side which allows you to implement new protocols. And then basically you would configure from your client side then your address, and here you would see how you would create a data tag, and you just have to give the name of the equipment to which should be responsible then later on to retrieve this information. Here I try to make a little sample about if you want to get the temperature of Malaga. So here I defined a post request, which you wouldn't normally do more. You would more fetch it from somewhere, but I couldn't find a nice open API that already gives you the temperature. But here basically you could pull from a little script, you could pull this information to this REST equipment. And and then you could annotate this with metadata. So for instance, geolocation, country, and so on. And this would be how you would do it from your configuration. And you would just update your tag, which we call temperature Malaga, and you would add this metadata that you define in a hash map. And this is then directly also added to Elasticsearch as a field, which makes it then very easy to search and extract the data. So we try to use a bit open source everywhere. Of course, if we want to go open source, we have to be based on open source products. And what we now changed is to make it more simple to start up prototyping, and we use Spring Boot in all the layers, which has this paradigm of convention over configuration. So by default, you don't have to configure anything. It would start up for you the database, an in-memory database. It would start up for you Elasticsearch. And so basically when you start up the server, you have a fully running service, and you can start prototyping and create your DACs. And we have also a nice web interface that comes with the system, which basically allows you then to see all your services that are configured. So this is now coming from production from us. You can see the availability of the system over the year, how many inputs you have, so tags that are coming through the system. So this is pretty low on that service. And you can see how much the data rates that are filtered out. So this is all coming with C2MON. And the interesting thing is really then to see your configurations of your different processes. So I can see here, okay, that is, on that process there's one equipment defined, but there could be several hundreds. Depends really how you set up your system. And then you can browse through all your configuration. And this can be very complex, as you can see here, for instance. So this is from a PLC, so it needs then to, this is a PLC hardware address, and normally then you have really cryptic names which are used, and path lengths and so on, and this is what you don't want to deal with it on normally by yourself. I just show you also an example of how we can then use Elasticsearch. So this is from this Diamond service. They are dealing with different computers and front ends. And this was now very easy to set up. It's like the data from, I don't know, from 30th of April up till now. And because everything is already structured, it was very easy to set up all the machines. And as you can see, it's just one, basically at the moment we have just one single Elasticsearch instance, but it can retrieve very fastly then the data. So, and it's just up to you how you set up your metadata and how you set up your tag naming structure to then achieve very easily such a dashboard. Right. Time is over. All right. Yeah, Tim. Okay, then I skipped him. Just maybe one last word where we are. I can show you more about what Tim does after the talk, if you like. This is the setup, how we have set up the service on our side. So we have many DACs and currently just 2 servers, which are for the redundancy, and then the different client application on the top. And what's coming next? So I said we are looking for collaborations, and we are working on providing also agents basically to replace the central data acquisition configuration. So you might want to have a mix when you are able to include an agent API on your process. You might want to send directly the sensor data to C2MON. Okay, here's a list of the technologies used, which you can then check offline once the presentation is available. And I'd like to thank you for your attention.
So lunch is close, but time for some questions if we've got any.
Nobody dares. Okay. Here, there's one.
I have one question about the products that you have at CERN.
Yes.
When you take it to the industry, the revenues that you get from that, it adds up to the 1 billion Swiss francs, or it's for the team that created, or who manages it? Who manage that revenues, if you get any revenues from those products?
You mean revenue with the product?
Technologies that you build at CERN and then goes to industry.
Well,
if you have patents,
there's just the pleasure of sharing, basically. So that's the good thing, because CERN is funded by tax money. So we're not looking to make money. It's more to give back really to the industry what has been developed at CERN. So it's really just that's why it should be interesting to collaborate with us, because you can have the assurance that it's working. It's like already battle tested on our side, and so yeah. And then basically somebody could start a spin-off with C2MON and just create some nice applications around that system. Yeah.
Okay. Thank you.
Yeah. Right. Anybody else? No. Okay. Thank you.
Thank you, Matthias.